For 30 years, the global scientific community largely looked at the blueprints for this process and dismissed it as an impossible pipe dream. When you zoom in on a modern microchip, you find a nanoscopic city, skyscrapers hundreds of layers tall, connected by hundreds of kilometers of wire. And at the very bottom of that labyrinth, you find billions of microscopic transistors, flipping back and forth to create the ones and zeros of our digital world. Since 1965, the entire tech industry has run on an observation made by Intel co-founder Gordon Moore. He noticed that the number of transistors you could fit onto a chip doubled roughly every 2 years. To make computers faster and more powerful, engineers just had to keep shrinking those transistors. Eventually, physics gets in the way. Engineers had to figure out how to physically print these transistor blueprints when the lines themselves were smaller than the wavelength of visible light. If they couldn't solve that shrinking problem, the economic growth of the modern world would stop. To understand how they pushed past that limit, you have to look at how chips are actually made. It starts with ultra-pure silicon, melted down and pulled into a massive single-crystal ingot, then sliced into thousands of ultra-thin, carefully polished wafers. Each blank wafer is then coated in a light-sensitive material known as photoresist. During the exposure phase, light passes through a patterned mask, a microscopic stencil. Where light strikes the photoresist, it weakens the coating. A chemical solution washes away those weakened areas. With the silicon exposed, high-energy plasmas carve physical lines deep into the wafer itself. Next, those etched grooves are filled with metal, like copper. And then, this exact sequence, coat, expose, etch, and deposit, repeats. Layer by layer, up to 100 times, the chip is built upward. For half a century, this elegant light printing cycle functioned flawlessly. It was the reliable engine that made our electronics continuously smaller and cheaper. By roughly 2015, the required features became smaller than the deep ultraviolet light being used to print them. You run into a physical phenomenon called diffraction. When you try to force light through gaps that are narrower than its own wavelength, the waves bend. They spread out and overlap, creating a blurry mess instead of a crisp line. To keep shrinking the patterns, there was really only one theoretical way forward, using extreme ultraviolet, or EUV light, which has a drastically shorter wavelength. Transitioning to EUV required solving severe physics problems that decades of research had labeled impossible. Without it, the exponential growth of computing was dead. The first problem is that EUV light doesn't exist naturally on Earth. Even if you make it, it is immediately absorbed by air. Engineers realized they would have to build an artificial supernova, and they would have to do it inside a vacuum chamber. To fuel this reaction, they use extremely pure liquid tin. High-pressure gas forces the molten metal through a microscopic, vibrating nozzle, breaking the stream into individual droplets. These liquid droplets are violently chaotic at first, but they quickly snap into perfectly identical shapes, uniformly aligned and flying forward at hurricane speeds. Then comes a dual laser strike. A preliminary pulse flattens the fast-moving droplet into a wider pancake shape. Microseconds later, a 20,000-watt secondary strike vaporizes the tin into a 220,000 Kelvin plasma, 40 times hotter than the sun, releasing the EUV light. To generate a continuous stream of light, the machine perfectly tracks and annihilates 50,000 individual droplets every single second. This controlled, rapid-fire chaos is the only known scalable way to produce the precise wavelength of light needed. Creating the light only addresses one part of the challenge. Traditional glass lenses absorb EUV light on contact, making all standard focusing optics useless. To corral this invisible light, they had to design curved mirrors built from alternating microscopic layers of silicon and molybdenum. Instead of passing through a lens, the light bounces off these surfaces. Because EUV wavelengths are so tiny, these mirrors must be atomically smooth. If the surface is even slightly rough, the light scatters randomly and the pattern is ruined. To put that smoothness into perspective, if you scaled one of these mirrors up to the size of the Earth, the largest physical bump on the entire planet would be no thicker than a single playing card. These flawless mirrors allow the intense radiation of those tiny supernovas to be captured, bounced off the stencil, and shrunk down onto the silicon wafer. Keep in mind the environment inside this machine. It is radiating heat from continuous plasma explosions, while mechanical parts whip back and forth at over 20 Gs, 5 times the acceleration of a Formula One car. Despite that vibration and thermal expansion, every single new layer printed onto the chip must perfectly align with the invisible layer already printed directly beneath it. To manage this, the optics module contains a built-in robotic nervous system. Specialized sensors constantly measure the exact position of the mirrors and adjust their angles in real time. They make these adjustments at picoradian precision. That is the mathematical equivalent of standing on Earth, aiming a laser pointer at the moon, and intentionally choosing which specific side of a dime you want to hit. Thanks to that constant robotic correction, the printed layers never miss their alignment by more than 1 nanometer. That is a margin of error of roughly 5 silicon atoms. By holding a 5-atom tolerance, engineers turned a violently shaking, heat-blasted metal box into the single most precise instrument in human history. When you zoom back out from the atomic scale, you see the massive physical footprint required to house this whole process on a cleanroom floor. The final, fully assembled machine costs around 350 million euros. It is constructed from 100,000 specific parts, connected by 3,000 cables and 2 kilometers of hosing. Just shipping one of these units from the factory to a customer requires 25 semi-trucks and 7 massive Boeing 747 cargo planes. It takes an extreme macro-scale logistical web, sprawling global supply chains, jumbo jets, and billion-dollar factories just to manipulate single atoms. Yet this complex sequence of lasers, supernovas, and flawless mirrors is happening continuously, right now, to manufacture the chips powering the smartphone in your pocket. The technology we rely on daily is the result of engineers who simply refuse to accept the absolute limits of physics.